All right, if you're in computer science, you've definitely come across this one. It's a data structure that pops up literally everywhere, from how your computer's OS works to some really clever programming puzzles. So today, we're going to break down the queue, what it is, how it works, and why it's such a fundamental tool in your coding arsenal.
Okay, so here's the game plan. We'll kick things off with the core concept, the FIFO principle. Then we'll get our hands dirty and look at building queues with arrays, and then a more flexible way to do it. And we'll wrap up by looking at where you'll see queues out in the wild.
So before we even touch a line of code, let's get the main idea down cold. Just think about any time you stood in line, for coffee, for a concert, whatever. The first person to get in that line is the first person to get served, right? That's it. That is the entire idea behind a queue. It's first in, first out. Simple as that. It's all about keeping things fair.
Okay, so let's put the textbook definition on it. A queue is just a collection of things where you follow two very strict rules. Rule 1, new stuff can only be added to the back. Think the end of the line. Rule 2, stuff can only be taken from the front. No exceptions. You can't cut in line, you can't sneak out from the middle. The order is everything.
And these 5 methods, they are the basic operations you'll use to work with any queue. What's cool is how they map one-to-one with our ticket line analogy. Enqueue, that's you getting into the back of the line. Dequeue, that's the person at the front finally getting their tickets and leaving. First is like peeking over everyone's shoulder to see who's up next without them actually leaving. And size and empty are pretty self-explanatory. They just tell you how long the line is and whether there's a line at all.
Okay, time to get practical. Let's actually build one. Now, if you're like most programmers, when someone says a collection of items in order, your first thought is probably an array, right? And yeah, that's a totally natural place to start. It's efficient, it's simple, but it also creates a couple of tricky problems we're going to have to figure out.
The initial setup is pretty straightforward. You've got your array, which is just a block of memory to hold the data. Then you need a couple of pointers, basically. We'll use an index, let's call it f, to always point to the front element. And we'll use a simple integer, maybe sz, to keep a running count of how many items are actually in the queue at any given moment.
But here's where we hit our first snag. Think about it. Every time you dequeue someone, that f index moves one step to the right. And as you enqueue new people, you fill up the array from the back. So what happens? The actual line of people starts to drift across the array. You end up with all this empty, wasted space at the beginning, but you're about to hit the end of the array and get an error, even though the queue isn't technically full. It's a weird situation.
So what's the fix? We've got all this perfectly good empty space just sitting there at the front. What if we could just loop back around? What if we treated the array less like a street and more like a racetrack, where the finish line connects right back to the start?
And that's exactly what we do. This is called a circular array. And the secret sauce here is a tiny but powerful mathematical tool, the modulo operator. You know, the percent sign? By calculating the next available spot using this formula, we make the array wrap around. When an index goes off the end, modulo brings it right back to the start. It's a super clever trick to use every single slot in our array.
Okay, the circular array is smart, but it has one major weakness, a real Achilles heel. The size of the array is fixed from the very beginning. You have to decide on its capacity up front. And that's a tough guess to make, right? If you make it too small, your queue overflows and your program breaks. If you make it too big, you're just sitting on a bunch of wasted memory. So if you don't know how big your queue needs to get, this approach can be a real problem. So if that fixed capacity issue is a non-starter for you, what's the alternative? Well, that brings us to a much more flexible, dynamic way of thinking about this, using a linked list. And this right here is one of the classic trade-offs in computer science. You're going to see this pattern again and again. With the array, you get super efficient memory access because everything is stored together in one nice block. But it's totally rigid. The linked list is the exact opposite. It gives you incredible flexibility. It can grow as big as you need it to, one element at a time. The downside? There's a tiny bit of memory overhead for each element because each node has to store a pointer to the next one in the chain. Now here's the best part. You don't have to reinvent the wheel. If you already have a good singly linked list implementation, building a queue on top of it is, well, it's almost trivial. Want to enqueue something? Just call add last on your list. Need to dequeue? Just call remove first. It's a beautiful example of code reuse. And just look at this Java code snippet. This says it all. The linked queue class isn't doing any of the heavy lifting with nodes and pointers. Nope. It's just acting as an adapter, it has a singly linked list inside it, and when you call a queue method like enqueue, it just turns around and delegates that call to the appropriate list method, in this case add lost. It's a really clean and elegant way to build things.
All right, so we've covered the theory, we know what a queue is, and we've got 2 solid ways to build one. But who cares, right? Let's talk about why any of this actually matters. Where are you going to see queues out there, solving real-world problems? Honestly, once you start looking, you'll see them everywhere. Queues are the unsung hero of managing shared resources. Think about a customer service call center. The first call that comes in is the first one answered. That's a queue. Or a shared printer in an office. All the print jobs line up and get printed in order. Even something like stock market accounting uses the FIFO principle. It's all about fairness and processing things in the order they arrive. But queues aren't just for practical stuff like printers. They're also amazing tools for solving some pretty mind-bending algorithmic puzzles. Let's take a look at a really famous one, the Josephus problem. This is a classic, and it's a perfect showcase for how a simple data structure can solve a tricky problem with style. Okay, here's how the puzzle goes. You've got a group of people in a circle. You go around the circle, and every, say, third person is eliminated. The last one standing wins. So how do you model a circle with a queue? It's genius. To go around the circle, you just dequeue an element from the front and immediately enqueue it to the back. You do that twice. The third person who gets to the front, you dequeue them and just don't put them back in. They're out. You just keep doing that. Rotate, rotate, eliminate, over and over until you've only got one winner left. So let's boil this all down. What are the key things you absolutely need to remember? First, the big one. Queues are all about that strict first in, first out order. Second, you've got 2 main implementation options: arrays, which are efficient but fixed in size, and linked lists, which are flexible but have a little overhead. Know that trade-off. And finally, remember what they're for. They're essential for managing resources fairly and for elegantly solving tricky algorithmic puzzles. But I want to leave you with one last question to think about. Turns out there's a pretty complex mathematical formula that can solve the Josephus problem instantly, no simulation needed. So why would any programmer bother writing the queue-based solution? Well, the answer gets to the heart of what it means to be a good developer. The simulation, while maybe slower, is incredibly easy to understand and write. The formula is dense and hard to prove. And a lot of the time in the real world, the clearest, most readable solution is actually the best solution, even if it's not the smartest one on paper.